Okay, welcome to the Journal Club for the Classics in Immunology once again. And this week we're going to talk about gamma interferon or immune interferon as a new cytokine that was first reported in 1965, exactly the same year that Kasakura and Lowenstein from last week and Gordon and McLean talked about a so-called what came to be known as a blastogenic factor. There was another paper in Science magazine. Their papers were in Nature. This one's in Science. Again, it's only 2 pages long. So you ought to check it out from the KendallASmith.com website under the writings tab. This is by a fellow by the name of Frederick Wheelock. And the title of the paper is Interferon-like Virus Inhibitor Induced in Human Leukocytes by phytohemagglutinin. So there's that phytohemagglutinin again. Peter Knoll talked about in 1960. So 5 years later, 1965, and in the interim, other people had, reported the same thing, and there was an explosion going on in leukocyte cultures and so forth. So to give you a little background on Wheelock, I actually met Wheelock when I was a young blade, just starting off in my business. Nice guy, hematologist, which is what I started off on. And he was an undergrad at MIT, and during World War II, and so his whole career got interrupted. He got into the army and so forth, and afterwards he came back and graduated around 1950. And then he went on to medical school at Columbia in New York City, graduated, got an MD, and went to the University of Rochester, New York, and did his house staff training and internal medicine and so forth. And then he went to the Rockefeller Institute, which is now the Rockefeller University in New York, and got a PhD. This guy was focused on science rather than medicine, very much like what happened to me. And he ended up being a hematologist and interested in leukemia and lymphoma and so forth. And his career spanned, like 40 years or so. And he just died in 1920 at the age of 93. But he was a Case Western in Cleveland. And then he was in Philadelphia at several different medical schools and universities, Thomas Jefferson, Hahnemann, Drexel, and so forth. And so he had a long career in this whole business. And early on, when he was just a young guy, and this is another one of these papers, but there's only one author. Nowadays, that's very unusual. You don't really read too many papers in science that are only one author and these things. But so it tells you a little bit about how the science was being done at that time. And so he takes off in the introduction as to why he focused on this virus or interferon-like virus inhibitor. He details in the introduction there was a phenomenon that was called virus interference initially. There was a paper out in 1952 by a fellow by the name of Stephen Fagekas de Saint-Groth and Isaacs, where 1952, remember now, that's before 53 when Meadoworth talked about his skin graft rejection and so forth. A lot of people, well, and it goes back to the days of influenza virus research. Everybody who was anybody was really doing influenza virus research. Fagekas de Saint-Groth was at the Walter and Eliza Hall Institute in Australia, and where Macfarlane Burnet became the director of that. And of course, Macfarlane Burnet is the one that showed for the first time that you could grow the virus, chicken egg embryos, injected through the shell and so forth. And so this was before tissue culture became a thing. And so Fagekas de Saint-Groth was able to show that when he used a heat-killed virus and injected it into the chicken embryos, and then waited for some time periods and took some fluid out of the chicken eggs, and then tested it, that he could show that there was something that was interfering with virus replication when he put it in new chicken eggs and that had been infected with virus and so forth. So that was 52. Then in 57, there was another paper out, and in the Royal Society of Proceedings of the Royal Society in London, by Isaacs again, who was Fashikat's mentor. He went on and continued on this whole thing. And he pointed out that the problem was when you were dealing with in vivo, in the embryo, in the egg, it was very difficult to do these kinds of experiments and manipulate them and get any meaningful data from them and so forth. And so he took amniotic membranes and cultured them in vitro in simply balanced salt solution and so forth. They were short-term cultures. This wasn't tissue culture when you took and put in a lot of other ingredients like sugars and amino acids and all the building blocks that you might need in order to grow cells and so forth. But he could do short-term experiments this way. And he simply repeated what Fashikats had done back, and he himself, Isaacs, had done before. And he did timed experiments then with adding heat-killed virus to these cultures and then measuring for interfering activity to other virus replication over time. And he was able to demonstrate that, or they were able to demonstrate that was the case. There was a postdoc that worked with him, was by the name of Jean Lindemann, and he was from Zurich in Switzerland. That paper then became the sine qua non for interferon. That was the first accepted demonstration that there was something that was happening inside those cultures that was interfering then subsequently with virus replication. And that was very important because people didn't have any therapies for viral diseases, and so that was the beginning. But this discipline, this interfering phenomenon and discipline became the virologists. That was their deal. That was their baby. Virology did it because and then they went on and they did all kinds of experiments and devised interferon assays in vitro and did detailed titrations of their interferon fluid and so forth that were very, very important for things that happened subsequently in the lymphokine field and so forth. Well, so that was already known. That was in the background. And what Wheelock started on is that by accident, he found he was doing the same thing with PHA, phytohemagglutinin, that the other investigators were doing to study the white blood cells. The cytogeneticists wanted to be able to look at the metaphase chromosomes under the microscope, and Wheelock was a hematologist, and he was interested in leukemia and lymphoma and that sort of thing. And he found that when he used PHA to separate the red cells from the white cells so that he could study the white cells, that there appeared in the soups of these things interferon-like activity. So it was sort of an accidental discovery. And he then, in this particular paper that came out in Science in 1965, he did more experiments to detail this whole phenomenon. Now, at the time, it was already known and had been published in 61, for example, by a fellow by the name of Ian Gresser, who was at Harvard with Enders, the guy who showed that it was possible to grow poliovirus in tissue culture. Ian Gresser had shown that you could take leukocytes from the peripheral blood of people and incubate them with viruses, and that you would get interferon-like activity. So the other experiments had been done in other kinds of cells and so forth. So the idea that was viruses would, and everybody said, well, big deal, because we know viruses cause the cells to make this interfering activity. But the importance of this particular paper in 1965 then was the fact that non-viruses could stimulate cells to make this interferon stuff. So in the materials and methods, he lays out in detail exactly what he did. He would take the leukocytes after separating them from the red blood cells, and he cultured them in vitro within what they called Eagle's minimum essential medium and fetal calf serum, and 2 million cells per ml, and that became sort of classic and standard. And he then would stimulate them with PHA or whatever he wanted to stimulate them with, either virus or PHA, and he would then assay in the soup of these cultures for interferon activity, and he assayed them on human cells, human fetal lung cells. Can you imagine doing that today without getting a permission from the Pope, I mean, it would never happen. And then also on baby hamster kidney cells, and then on mouse skin fibroblasts. So he had 2 different species and then humans. When he tested the soups on lung cells, these soups from the PHA stimulated leukocytes, he got positive reactions in terms of interferon activity, but it didn't work on baby hamster kidney or the mouse fibroblasts, which is what one of the characteristics of what interferon was. It was always species specific. Got a human source on human cells and mouse on mouse and so forth. He also used the same thing that Gresser had done, and he used the leukocytes and stimulated them with virus, and then took those soups so that he would have the sort of the classic interferon-like substance to compare with this PHA-induced product. What he found was that when he used PHA, he could measure interferon activity in these soups within 2 hours. So there was a 2-hour lag time. It just didn't happen, instantaneously. And then it would increase over time, over the next day or two, peaking around 20 hours. And he could show that the lung cells that he tested the interferon activity, if he just added PHA to them, nothing happened. There was no interferon activity. And he could also show, he assayed for virus in the leukocyte cultures before he added things, and there was no virus in there. So the virus was sort of swept out of the picture early on in these experiments. And when he compared the characteristics of the interferon-like activity that from either induced by viruses from leukocytes or PHA from leukocytes, the virus induced interferon, you could spin it in the ultracentrifuge at 100,000 times gravity for 2 or 3 hours, and you would not lose the activity. You would stay in the liquid phase of the whole thing. So that was not, it was non-sedimentable at 100,000 G. You could expose the virus-induced interferon to low pH, acidic conditions, or very alkaline conditions, and the interferon activity was not destroyed. And you could also then incubate it with trypsin, which is an enzyme that chops up proteins, and it wasn't destroyed by trypsin either. So those are the characteristics of the so-called classic interferon. And when Wheelock looked at this PHA-induced stuff, it was different. It was non-dialyzable, so it was a bigger molecule than would go through a dialysis membrane, and he couldn't take it out with the ultracentrifuge. So it was up in the supernatant. It was a molecular something, a bigger molecular something in the supernatant, but it was labile to acid and alkaline pHs. He could heat the PHA-induced interferon, and he could destroy the activity with heat as well. So that made it different from the virus-induced stuff. So that was it. Now, and that's it in the paper. There's only one table in the paper with pluses and minuses and so forth, depending on what he tried to do to the thing. So it's easier to hit it big in those days back in the day. Huh? You could go in Science and Nature and whatever else. So in the discussion of the paper, he pointed out that other non-viruses could also induce interferon activity, and one of them in vivo, particularly bacteria, if you infected an animal with bacteria, you could get interferon activity. And also endotoxin, bacterial lipopolysaccharide, LPS, in vivo would cause the appearance of this interferon-like activity. And then the synthetic nucleic acids, poly-IC, poly-AU, which are synthetic double-stranded RNA molecules that were used to try to mimic the genome of viruses and so forth, that would induce interferon activity. And in the discussion of the paper, Wheelock said that he couldn't be completely 100% positive, but it looked like it was coming from the lymphocytes. It was still up in the air, whether it was monocytes or lymphocytes or in large cells, small cells, and so forth. And he references a review that had come out, I think also in Science, about these lymphocytes at the time. And even then, and this review was published in 1964, just a year previously, they point out that it's still sort of unknown what these lymphocytes really do. And they speculated that they might even change into antibody forming cells, which is true. You have to be a B cell first, though, in order to become a plasma cell to make antibody. And so things were still pretty wishy-washy back in the first part of the 60s in terms of what these lymphocytes were doing. And this paper, I decided to focus in on it itself, because it really was in addition to the two I talked about last week on blastogenic factors, this paper on interferon activity, which subsequently started to be called immune interferon to separate it from the virus-induced interferon. That meant that these cells were making more things than that met the eye. And this brought in other investigators and brought all the virologists into the immunological circles. They wanted to keep themselves separate, still do, but which has been one of the things in this whole COVID pandemic. The virologists look at the elephant from their corner, and the immunologists look at the elephant from their corner, and so forth. But this was really the beginning of the whole lymphokine, cytokine saga that I'm going to tell you a lot more about as we move forward. So that's it. And so just like before, if you haven't already signed up on the YouTube site, subscribe, ring the bell, and also go on the website and go into the writing section particularly. And all the classic papers of immunology are there. And so you can, when you can't sleep at 3 a.m, you can read those too. And it's fun to then to read the paper before we discuss it. And this one will be coming out on Monday. And so that's what the 16th said, 18th of April. And I'll stop there. Thanks for listening. It's been fun.